In the first picture here, you see a schematic diagram of the torsion balance. The two small green lead spheres attached to a horizontal crossbar, which is suspended in the middle by a very fine torsion fiber, really a very fine wire. Attached to the torsional pendulum is a small mirror. When there are no large spheres in place to exert any kind of gravitational force or torque, notice that the laser beam is aligned so that it experiences no horizontal angle of deflection before hitting the screen. In the second picture, you see that the two large lead spheres, symbolized in yellow here, are brought into the position shown. The gravitational force and torque between each large sphere and small sphere causes the wire to oscillate, which in turn will cause a laser beam to slowly oscillate across the screen with smaller and smaller oscillation amplitudes until it ceases to move at all. That's when a new equilibrium has been reached. In this picture you're looking at in the right-hand portion of your screen, you're seeing the actual laser that is used in the MJC physics lab to collect the data for this experiment. And then finally, in the picture in the lower right, you see a diagram of the Cavendish balance in the MJC laboratory. Notice that the torsion balance is inside a glass case, in order to prevent air currents from exerting any kind of external forces on it. You can't really see the torsion wire because it's too thin, but you can see the laser light reflected from the mirror, that is attached to the wire. Now, this animated GIF shows you that when the massive lead spheres are far from the smaller lead spheres, such that there is very little gravitational force and torque, there is no horizontal angle of deflection of the beam. But when the large spheres are brought into the close position next to the smaller lead spheres, a sufficient gravitational force and torque exists on the smaller spheres, to cause them to start oscillating, in which case the laser beam now oscillates back and forth on the screen. For our experiment, the distance between the balance and the screen is many meters. While the actual oscillations of the pendulum are quite slow, this time-lapse video clip speeds up the time so that you can see how the apparatus can be used to collect data. You can see here that the amplitude of oscillation is quite large at the start. Look on the screen how far the laser beam is moving. But these oscillations will gradually decrease in time, as the oscillations continue. When the system reaches its new equilibrium position several hours later, the horizontal deflection of the beam on the screen can be measured from its initial equilibrium position to its final equilibrium position. And finally, in this last slide here, you can see how the computer is used to trace the oscillations of the pendulum. From this sinusoidal graph, the period of oscillation can be accurately measured. You can see that the amplitude of oscillation, and thus the horizontal trace on the screen, will gradually decrease in time, as the new equilibrium is established with the spheres in their new positions. And you can see here on this slide how we can pretty accurately figure out the period of oscillation, from this computer-generated graph here, simply by finding the time between two successive peaks on the graph.